Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving an interesting trigonometric equation with complex numbers. We have cosine z minus I sine z equals 1 over e, and we're going to be solving for z values. What else could you solve for, right? Z is a complex number, and what does that mean? If you're new to complex numbers, go ahead and check out my lecture videos. If you like algebra, number theory, and trigonometry problems like this one, go ahead and check out Cybermath, my very first channel. You could also consider joining the channel by clicking the join button at Cybermath. Great, so let's go ahead and take a look. We have this equation, and if I said that z is complex, right? But obviously complex numbers also include real numbers, right? And if z was real, which means it cannot be like a plus bi where b is different from 0, then we would be getting like two numbers that are equal, right? So when is a complex number like a plus bi, by the way, that's the name of this channel, so easy to remember, hopefully, is equal to something like c plus di, this implies two things, a equals c and b equals d. Why? Because if you put everything on the same side, you're going to get something like this. And how can a complex number be equal to 0? It has to be 0 plus 0i. Exactly, right? Both of these have to be 0. Okay, then can we write the right-hand side in the standard form, a plus bi form? Sure, we can. So let's go ahead and give it a try. Cosine z minus I sine z is equal to 1 over e. We could probably write it as 1 over e plus 0i, right? So this becomes the real part, 1 over e, and this becomes the imaginary part. And from here, we can safely say that, in this case, cosine z needs to be 1 over e, and sine z needs to be 0. But Houston, and all the other states, we have a problem. Why? Because if cosine z is 1 over e, whatever angle makes it that way, right? That's fine. And in this case, notice that z can be real because 1 over e is less than 1, so it kind of falls in that interval. And when cosine z is 1 over e, sine z cannot be 0, because think about it. No matter what z is, cosine, like real or non-real, sine squared plus cosine squared is always equal to 1. Always, always, always. Okay? So what does that mean? That means that if this is true, then cosine needs to be 1 or negative 1. But that's not the case. So we arrive at a contradiction, which means that this can't be happening. But what is that supposed to mean? It just means that z is not real. Because if z were real, or was real, however you like it, then this would be true, which is not true. So z is not real. Well, what does that mean though, right? I mean, that probably means that you can replace z with something like a plus bi, or you can do r times e to the I theta. Thanks to Euler, we have a polar form for a complex number, which is actually pretty compact. It's beautiful because if you have two complex numbers, like let's say r e to the I theta and r prime e to the I alpha, you could actually multiply them. So easy. Multiply the moduli and multiply these two exponentials, add the exponents, and you get another exponential, so on and so forth. So that'd be fairly easy, right? But so second form needs to be, I mean, it looks like it's a better candidate, but you can try both. But it kind of comes down to this. Okay, let's rewrite the original problem. Cosine z minus I sine z is 1 over e. We have a complex number on the left-hand side, but a real number on the right-hand side. So the left-hand side also needs to be real. So what can we do? If you replace z with this, r e to the I theta, then we should be getting something like, let's see, cosine of r e to the I theta minus I sine r e to the I theta. That doesn't seem to be helping much, does it? No? Okay, so then maybe we'll scratch it out and try the other version. How about this? Cosine a plus bi minus I sine a plus bi equals 1 over e, right? Well, from here we have some formulas. Well, what's cosine and alpha plus beta, right? You get cosine a cosine bi minus sine a sine bi. Remember, it's the opposite. If you have a plus sign, it turns into a minus sign. And for this one, we can write something like sine of A. Oops, actually I should start with cosine probably. No, actually it's the other way around. Yeah, sine of A cosine of BI. And then plus will be plus sine of BI cosine of A. Well, does this help at all? Well, a tiny bit. The problem here is the cosine of BI. How do you find cosine of BI? Or in general, what is cosine of A plus BI, right? How do you cosine a complex number? I mean, you probably know how to find cosine of pi over 2, pi over 3, or any angle with a calculator, cosine of 10 degrees. You can find using a calculator, right? Hopefully, in degrees, I mean. So, but when it's complex argument, that's very problematic and very complicated, right? So we kind of have to do something else, or maybe not. Because if you think about the two versions of these, there's actually another one, which is this one. Z can also be written as R times cosine theta plus I sine theta. And where does this come from? This comes from Euler, thanks to him, because he's the best, in my opinion. E to the I theta, he discovered that these two things are equivalent. And it's I think, a huge discovery. And the most beautiful equation in math comes from here. That's why it's amazing, right? And many other things, of course. But what is that supposed to mean? Well, maybe we can use this form. Okay, let's go back to the original. Cosine z minus I sine z equals 1 over e. Great. So look at the left-hand side. Now we know that this is equal to e to the I theta. So can we make the left-hand side look like that? I mean this one? Sure, with a little manipulation and a little bit of knowledge of trigonometry, which is necessary. If you're doing complex numbers, you need to know a lot of trigonometry. Pre-calculus, definitely calculus, right? So here's how it goes. Sine is an odd function. So sine of negative z is a negative sine of z. Make sense? So we can replace negative sine of z with sine of negative z, but cosine of negative z is same as cosine of z. Think about it. On the unit circle, you have two angles that are opposite or symmetrical with respect to the x-axis. Their cosines are equal. Great. So let's do this. Replace cosine z with cosine negative z and negative sine z with sine of negative z. And guess what? You find your theta. Yes, this is your theta. So e to the power I theta. There you go. That's your number. So we were able to convert something that looks complicated, something that is trigonometric and imaginary or whatever, to an exponential, which is awesome. That's why Euler is awesome, okay? Don't forget that. Now we have that on the left-hand side, but we have 1 over e on the right-hand side. So let's go ahead and put them together, where they'll be happy. E to the power I times negative z equals 1 over e. And you might still be questioning, like, what are we going to do from here? Don't worry, I'm going to go ahead and show you every single step, so stick around. Now, 1 over e can be written as e to the power negative 1, right? Not negative I, e to the power negative 1. Awesome. So now we have two exponentials that are equal. So can I safely say that I times negative z is negative 1? Yes and no. So we got to be a little careful. So let me go ahead and show you so you don't miss any of the solutions. And guess what? If I did not forget to include solutions from Wolfram Alpha, we're also going to check them out. I think I remember to do it. Anyways, so this is what we have so far. But don't set them equal to each other, because in the complex world, we have something called e to the power 2 pi n I. And you know what that is? It's equal to 1. So this is the complexification of 1. Ta-da-da-da. Again, for the same reason, if you look at the Argand plane, which is a fancy name for the coordinate system, but you call this imaginary axis, you call this real, and plot numbers as points or vectors, right? So in this case, the angle is going to be a multiple of 2 pi. So your angle is going to be right here. And the modulus, whatever the modulus is, it could be 1 in this case, I guess, right? So that's your number. And that is 1, because it's 1 unit away from 0, and it's positive. You see? So this is equivalent to 1. But why did we do that? We don't want to miss any of the solutions. That's why. So let's go ahead and do this now. We're going to go ahead and add these exponents so that we're not missing anything. You see? You have to have that. Now we can set those equal to each other. I times negative z equals negative 1 plus 2 pi n I. Now I want to get z, so why don't we just write this as negative I times z equals this. And finally, divide both sides by negative I, or I have a better idea, multiply both sides by I. It's a lot easier. Look, if you multiply negative I by I, you're going to get negative I squared. Oops, I forgot to say that. I squared is equal to negative 1. Therefore, negative I squared is equal to positive 1. Another piece of knowledge that you need to know. So z, these two cancel out, gives us 1. Z equals this. So z can be written as, if you distribute it, we're going to get another I squared here, which is going to be negative 1. So it's going to be like negative 2 pi n, and then minus I. So those should be all the solutions. And guess what? You can plug it in and test it out. But let's go ahead and check with Wolfram alpha, all right? So that's my solutions. And I'm going to come back and maybe just compare those two results. Uh-oh, Wolfram alpha, you really messed up this time. Well, it's just a lousy LLM. What can you do, right? Anyways, we're still smarter. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Let me know what you think. And don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out Cyber Math and A+BI. And bye-bye.